3.8. Derivatives of inverse functions and logarithms. The outline of this video is as follows. We will discuss a general method for finding the derivatives of inverse functions, which will provide a powerful new tool for our calculus toolkit. Then, we will immediately apply this general rule to a crucial specific case, finding the derivative of the natural logarithm functions. This result enables a new technique called logarithmic differentiation, which is a clever way to find derivatives of complicated functions, particularly those involving products, quotients, and exponents. We will then use this technique to prove the general power rule for any real exponent, extending a rule we have used in a more limited form. Finally, we will take a deeper look at the fundamental constant e, exploring its definition as a specific limit, which will connect back to our work with exponential and logarithmic functions. This progression will take us from a general theorem to its most important applications. Let us begin by establishing the core relationship between a function and its inverse. Their derivatives are reciprocals of one another at corresponding points. I will use a simple linear function to make this concept concrete. Let us take the function f of x equals 1 half x plus 1. Its derivative, which is its constant slope, is simply 1 half. Now the inverse of this function is f inverse of x equals 2, x minus 2, and its derivative is 2. As you can see, 2 is the reciprocal of 1 half. This algebraic result has a direct geometric meaning. When you reflect a non-horizontal line across the line y equals x to get its inverse, you are geometrically inverting its slope. The essential takeaway is that the slope of an inverse function is 1 divided by the slope of the original function at the corresponding point. This slide establishes the powerful reciprocal relationship between the slopes of a function and its inverse. Let us say we have a point, a comma b, on the graph of our original function f, where the slope is given by the derivative, f prime of a. The inverse function, f inverse, will then contain the corresponding point, b, a, with the coordinates swapped. The key insight is that the slope of the inverse function at this new point is the reciprocal of the original slope, meaning it is 1 divided by that original value. This gives us the formula. The derivative of f inverse evaluated at b equals 1 divided by the derivative of f evaluated at a. For example, if the slope of a curve at the point 2, 4 is exactly 4, then the slope of its inverse at the point 4, 2 must be 1/4. The essential rule to remember is that derivatives of inverse functions are reciprocals at their corresponding points. Now I will show you a powerful theorem that let us find the derivative of an inverse function, often without even needing a formula for the inverse itself. This rule, called the derivative rule for inverses, states that if a function is differentiable and its derivative is never 0 on an interval, then its inverse is also differentiable. The key insight is that the derivative of the inverse function at an output value, let us call it b, is the reciprocal of the original function's derivative. Critically, we must evaluate the original derivative at the corresponding input point, a, which is the inverse of f at b. For instance, the function f of x equals x squared has a slope of 4 at the point 2, 4. Its inverse, the square root of x, has a slope of 1/4 at the corresponding point, 4, 2. The essential thing to remember is that the slopes of a function and its inverse at these corresponding reflected points are simply reciprocals of each other. Let us confirm our new derivative rule for inverses with a familiar example to build our confidence in the formula. I will use the function f of x equals x squared for x greater than 0, whose inverse is f inverse of x equals the square root of x. We already know their derivatives are f prime of x equals 2x, and the derivative of the inverse is 1 over the quantity 2 times the square root of x. Now, applying our theorem, the derivative of f inverse is 1 over f prime of f inverse of x. This simplifies to 1 over 2 times the square root of x, which is exactly the result we already knew. We can also test this at a specific point. On the original function, at x equals 2, the y value is 4, and the slope is also 4. The theorem correctly predicts that for the inverse function, at x equals 4, the slope must be the reciprocal, or 1/4. This example shows that the rule works both for the general formula and for specific points. Here is an excellent practical application of our inverse derivative rule, where we find the derivative's value at a specific point without needing a formula for the inverse function. We want the derivative of the inverse of f of x equals x cubed minus 2, evaluated at the point x equals 6. Our first step is to find the input, which we will call a, for our original function that produces the output 6. By simple inspection, we can see that f of 2 equals 2 cubed minus 2, which is 6, so our value for a is 2. Next, we find the derivative of the original function, f prime of x, which is 3 times x squared. We then evaluate this derivative at our point a equals 2, which gives us 3 times the quantity 2 squared, or 12. The derivative of the inverse at 6 is simply the reciprocal of this value. Therefore, our final answer is 1 over 12. The key is to find the corresponding input for the original function and then take the reciprocal of its derivative at that point. Now we can apply the inverse function rule to find the derivative of one of the most important functions in calculus, the natural logarithm. We begin by remembering that the natural log of x is the inverse of the exponential function e to the power of x. Our rule states that the derivative of an inverse function is 1 over the quantity f prime of f inverse of x. For our case, the original function f is e to the x, so its derivative is also e to the x. Substituting this into the rule gives us 1 divided by e raised to the power of the natural log of x. Since the exponential and natural log functions are inverses, they cancel each other out, so e to the power of the natural log of x simplifies to just x. This leaves us with the wonderfully simple result that the derivative of the natural log of x is 1 over x. For a positive function u, the chain rule extends this to 1 over u times the derivative of u. Let us see how our chain rule for logarithms works with a few key examples, which reveal some useful and sometimes surprising patterns. First, consider the natural log of the quantity x squared plus 3. Here, our inner function u is x squared plus 3, and its derivative is 2x. Applying the rule, we get 1 over u times the derivative of u, which results in the fraction 2x over the quantity x squared plus 3. A more general case is the derivative of the natural log of the absolute value of x. Whether x is positive or negative, the result neatly simplifies to 1 over x, as long as x is not 0. Similarly, when we find the derivative of the natural log of b times x, where b is a constant, the chain rule gives us 1 over bx, all times b. The b terms cancel, leaving us with 1 over x. The important takeaway is that multiplying the input of a logarithm by a constant does not actually change its derivative. Now I will show you how to find the derivative of exponential and logarithmic functions for any base, not just the natural base e. The key insight for an exponential function like a to the power of x is to first rewrite it as e to the power of the quantity x times the natural log of a. Applying the chain rule, the derivative is e to that same power multiplied by the derivative of the exponent, which is simply the constant natural log of a. This simplifies our result to a power of x times the natural log of a. For a logarithmic function, we use the change of base formula, writing log base a of x as the natural log of x divided by the natural log of a. Since 1 over the natural log of a is just a constant, the derivative becomes 1 over the quantity x times the natural log of a. The main takeaway is that by using our knowledge of base east as a bridge, we can easily find the derivative for any base. Now I will introduce a powerful technique called logarithmic differentiation, which helps us find the derivative of very complex functions, especially those involving many products, quotients, or powers. It is the only way we can handle functions where both the base and the exponent contain a variable, like a function f of x raised to the power of another function g of x. The process works in 4 main steps. First, we take the natural logarithm of both sides of the equation. Second, we use logarithm properties to expand and simplify the expression, which cleverly turns multiplication into addition and exponents into simple coefficients. Third, we differentiate both sides implicitly with respect to x. Finally, we algebraically solve the resulting equation for the derivative, dy dx. This method transforms a difficult differentiation problem into a much more manageable one by simplifying the expression before you begin. Let us walk through an example of logarithmic differentiation, a powerful technique for finding the derivative of functions with complex products, quotients, and powers. Our function is y equals the quantity x squared plus 1 times the square root of x plus 3, all divided by the quantity x minus 1. The first step is to take the natural logarithm of both sides, which allows us to use logarithm rules to break the expression into a much simpler sum and difference of terms. Next, we differentiate both sides implicitly with respect to x, remembering that the derivative of ln of y is 1 over y times dy dx. After differentiating each term on the right, we solve for dy dx by multiplying the entire right side by y. The last step is to substitute the original expression for y back into the equation to get our final answer. This method helps us avoid a very messy combination of the quotient and product rules. Now I will show you how we can use logarithms and exponentials to prove a much more general version of the power rule for derivatives. This is a powerful step because it extends the rule to work for any real number exponent, including irrational numbers. The key is to start with a new definition for x to the power of n, which is e raised to the power of the quantity n times the natural log of x. To find its derivative, we can apply the chain rule. The derivative of e raised to some power is just e to that same power multiplied by the derivative of the exponent itself. The derivative of n times the natural log of x is simply n divided by x. When we substitute our original definition back in and simplify the terms, we arrive at the familiar formula. This means the rule for x squared also works for x to the power of pi. The essential result is that for any positive x, the derivative of x to the power n is n times x to the power of n minus 1. Let us now use logarithmic differentiation to find the derivative of a function where a variable is raised to a variable power, like y equals x to the power of x. Our standard differentiation rules for powers or exponentials do not apply here because both the base and the exponent are variables. The key is to first take the natural logarithm of both sides, which simplifies the expression to the natural log of y equals x times the natural log of x. Next, we differentiate both sides implicitly with respect to x. The left side becomes 1 over y times dy dx, and applying the product rule to the right side gives us the natural log of x plus 1. To get our final answer, we solve for dy dx by multiplying by y and then substituting back the original expression. This yields the derivative, x to the power of x, times the quantity, the natural log of x plus 1. Remember, this logarithmic approach is the proper way to handle functions with a variable in both the base and the exponent. We can also define the number using a very important limit, which we can prove by starting with the derivative of the natural logarithm. Let us begin with the function f of x equals the natural log of x. We know its derivative is 1 over x, so the slope of the tangent line at x equals 1 is exactly 1. Now, if we write out the limit definition for this derivative at x equals 1, we get the limit as h approaches 0 of the fraction with natural log of the quantity 1 plus h in the numerator and h in the denominator. Using a logarithm property, this can be rewritten as the natural log of the limit of the quantity 1 plus h, all to the power of 1 over h. Since we know this derivative equals 1, the expression inside the logarithm must be equal to e. By exponentiating both sides of that equation, we isolate the limit itself. Therefore, the number e is precisely the limit of the quantity 1 plus x to the power of 1 over x, as x approaches 0. Let us briefly summarize the powerful new differentiation tools we have just developed. We started with the fundamental rule for an inverse function's derivative, which is the reciprocal of the original function's slope at the corresponding point. This principle helped us find the derivatives for several important functions: the natural logarithm, the general exponential function a to the power of u, and the general logarithm with base a. We also learned a valuable technique, logarithmic differentiation, which is especially useful for complex expressions involving products, quotients, or functions with a variable in the exponent. Finally, we confirmed that the power rule holds for any real number exponent, and saw how the number e can be formally defined as the limit of the quantity 1 plus x, all to the power of 1 over x, as x approaches 0. These tools collectively give us the ability to differentiate a much wider range of functions. To wrap up, let us look at 2 review questions that will help you solidify the powerful techniques we have covered. The first problem asks for the derivative of an inverse function at the point 4, which is a direct application of our main theorem. Remember, you do not need to find an explicit formula for the inverse function itself. Instead, you will need to find the input value for the original function that gives an output of 4, and then use the reciprocal of the derivative at that specific input. The second problem involves a function where x appears in both the base and the exponent. Y equals the quantity cosine of x, all raised to the power of the natural log of x. This structure is a clear signal to use the technique of logarithmic differentiation. Working through these examples is an excellent way to test your understanding of these 2 important differentiation methods,